This type of solar water heaters is about 10 times cheaper than these solar collectors, and we can manufacture these cheap solar heaters quickly and easily, and therefore they can be interesting if we need a large solar station of several tens, hundreds or thousands of square meters of solar heaters. But unfortunately, they are not able to heat water to high temperatures, and this is one of my experiments when the sun heated the water to a temperature of 85 degrees Celsius. However, the maximum heating temperature may be less than 50 degrees Celsius in December or January. Let's together come to the idea of such a solar water heater, and we start from this very cheap heater, which consists of this wooden frame, a layer of expanded polystyrene, and this sleeve of black film which is filled with water. We know that this primitive solar heater can heat its water to a temperature of 70 degrees Celsius on a sunny summer day, but the heating temperature drastically decreases in the autumn, and now we see that the sun heated the water only to 41 degrees Celsius in Ukrainian October. Now let's add these parts with such a dark surface, and we see that this is a layer of expanded polystyrene with a wooden frame, and we also cover our heater with transparent polyethylene film. And now I show that the sun has already heated the water to 74 degrees Celsius. Unfortunately, Ukrainian November reduces the maximum heating temperature lower than 50 degrees Celsius, and this fact made me increase the thickness of this polystyrene. And so now the sun has heated the water to a higher temperature. Of course, we can additionally increase the maximum water temperature by several tens of degrees, if we use glass sheets instead of the transparent film. Or our solar heater has 2 glass sheets. Or we use cellular polycarbonate, and I plan to do similar experiments in the next winter season. We see that this surface is a black hole, which means that our solar heater absorbs solar radiation very well, and this solar radiation is absorbed by the black film of the sleeve, and its energy becomes the heat of the water. However, this reflected solar radiation is absorbed by this dark wall. At the same time, this solar radiation is absorbed by this dark wall, but its reflected part goes in the direction of the black sleeve, which absorbs it and converts it into heat of the water. So, this dark wall absorbs a lot of solar radiation, and therefore it is heated to a high temperature, and its heat is transferred to the water of the black sleeve through heating this air and through infrared radiation. I remind you that this is a relative of our solar heaters, and I already described it in 2 of my old videos about a year ago. Obviously, the width of our heater should be equal to the width of this polymer sleeve, and its length can reach several tens of meters if the terrain allows us to do such alignment of the surface of the heater, as it was described in my old video a year ago. However, I remind you that we must add this northern wall and these wooden battens. In addition, we must add this transparent film on these side walls, and our new solar heaters should be located along the east-west line. Besides, we must increase the length and thickness of these beams so that a strong wind does not overturn our new solar heaters. Energy parameters and construction cost of our solar heater are calculated in relation to the area of this rectangle, and they depend on this angle, on the proportion of these lengths, and on the thickness of the expanded polystyrene of this northern wall and this bottom wall. If this angle is 90 degrees, then our solar heater requires these materials, and we can calculate that it is about $6 per square meter of that rectangle of the transparent film, but the cost will increase if that angle is smaller or the thickness of the polystyrene is greater. I remind you that I am located here, at 50 degrees north latitude. This was my first prototype, and it had these principal dimensions, and the thickness of the expanded polystyrene of its north and bottom walls was 4 centimeters. And we see that it heated the water to a temperature of 84 degrees Celsius. Then I reduced this principal dimension, and we see that now the maximum water temperature is almost 85 degrees Celsius, and it was in the middle of Ukrainian September. This is my third experiment, but in the middle of October, and it turned out that the sun heated the water to a temperature of 74 degrees. Unfortunately, the closer to December, the lower the heating temperature, and now it is the middle of November, and we see that the maximum water heating temperature is 46 degrees Celsius. Then I reduced this principal dimension, and now it is almost winter, and the sun heated the water to a temperature of only 39 degrees Celsius. After that, I increased the thickness of this expanded polystyrene to 10 centimeters, and the thickness of this polystyrene layer was increased to 8 centimeters, due to which the heating temperature increased, and now my sixth experiment shows that the maximum water temperature is almost 64 degrees Celsius. This is my measurements of the energy parameters of my solar heaters during those 6 experiments, and we can see that they are worse than these parameters of expensive flat-plate solar collectors, but our heaters are several dozen times cheaper. I remind you that one of my old videos more than a month ago described how engineers use these parameters for prediction of heat production of various solar collectors and their thermal capacity. Let's take a closer look at these 3 of my experiments which were done with this same solar heater, but in different months. It is those 3 experiments, and this column reports the height of the sun above the horizon at noon, and these results can help us predict changes in the energy parameters due to changes in the height of the sun. Now we pay attention to these 2 pairs of my experiments, and these are comparisons which allows us to understand the changes in the energy parameters when we replace this solar heater with this heater, and then with this heater. In addition, this pair of my experiments is also interesting, and this is its comparison which shows the change in the energy parameters due to the increase in the thickness of the expanded polystyrene from 4 cm to 8 and 10 cm. Unfortunately, my experiments do not allow us to predict the energy parameters for cases when this angle is more than 90 degrees, or for cases of a big difference between these dimensions. This table shows how much heat is produced by 1 square meter of our solar heater for 1 year, and it shows the cost of our solar heat for the United States, India, and Europe, and it is obvious that our cost depends on this cost of capital and labor, and we see that the higher the heating temperature, the less the annual heat production, and the higher the cost of the solar heat. This cost of our heat is approximately equal to the cost of heat from natural gas, and these cases correspond to very cheap solar heat which is about 10 times cheaper than gas. This is an example of calculating the cost of our heat, but it is obvious that it will be true if our spending money and time reaches these targets. However, the production of heat with a temperature of about 70 degrees Celsius will significantly increase our operating costs due to the shorter lifespan of the polymer films, and due to such air bubbles which will be described in a few minutes. So, these were the calculations for the case of such solar heater when this angle is 90 degrees, and the thickness of its polystyrene is 5 centimeters, but obviously, the optimal values of these angles depend on our geographic latitude, and the closer to the equator, the greater those angles, and therefore the tropics may require this angle to be more than 90 degrees. I described the features of the connections in my old videos on these simple relatives of our solar heater about a year ago. Unfortunately, we can come to the conclusion that the connection of our solar heaters to pumps and tanks is not simple and easy. That is why I do not recommend using our type of solar heaters for cases when we do not need a large solar station, or if we do not have practical experience in the use of any solar collectors. Moreover, the connections will be even more complicated if we want to exploit our solar heaters during frosts, and I will describe their features of the connections in my future video on these more expensive but more efficient solar heaters. In addition, that future video will describe my technical tests how our solar heaters withstand snow. Of course, we must make replacements of these polymer films every 1 or 2 years, and first we tear off the old transparent film. Interestingly, the sun destroys only the upper half of the black sleeve, and now I am showing small holes which appear due to the destruction of the polymer by solar radiation. And these holes are telling us that this black sleeve will die in a few weeks. At the same time, the lower half of the sleeve is still in good condition, and we can use it as the stark surface of the north wall. Therefore we take this old black sleeve and fix it here, on the north wall, with staples. Now I am showing that the black film on the north wall will gradually grow old, but such damages have almost no effect on the efficiency of our solar heater. Then we put new black sleeve and connect it to water inlet and outlet. After that, we install a new transparent film, and now I show one of variants for fixing its edges with ease staples. Unfortunately, the rain does not wash away all dirt from the surface of the transparent film, and therefore washing the film in a few months may be desirable. In addition, sometimes we need to remove these air bubbles, and we see that this operation is very easy for the case of this relative of our solar heaters, but it is obvious that this operation will be more difficult for our case, and now I am showing how we can remove the bubbles through the side walls of our heater. Obviously, these wires will be inside the solar heater until the next operation of the bubble removal. And I want to add that the problem of the bubbles will be less if the heating temperature is low, or if we use industrial water which was made through deaeration.